All right. Hi, everyone. So I'm going to get started now. Today we're going to have discussion 10, which is about graphs. As you may notice, I'm in a different place today. I'm visiting some family, so I'm in a hotel. Anyway, so yeah, graphs today. So our objectives are to talk about graphs, right? So some properties of graphs, including cycles, connected graphs, weighted graphs, directed graphs, so just different kinds of graphs. And graphs are just an extension of trees. We talked about trees in the past, so hopefully today, if you haven't seen graphs before, it won't be too much of a difference. It's all the same things of trees, pretty much. It's just we're adding to it by just saying, okay, it doesn't have to be a tree, just more general. We'll talk about how we represent graphs with adjacency lists and adjacency matrices. We'll talk about traversals, which are depth first search and breadth first search, and we've seen these before with trees. And at the end, we'll just practice questions. So some properties of trees first. So first of all, graphs are data structures that consist of a finite set of vertices and edges. So yeah, just vertices and edges. Just like with trees, we had vertices and edges. But graphs, with trees, you're always guaranteed to have like, if you, so the number of vertices and edges are indicated by like V and E. This is just like the cardinality of the set of vertices and the cardinality of the set of edges. With trees in particular, trees are what we're going to call connected graphs. We'll talk about connected graphs on the next slide. But trees are a special kind of graph where E, like the number of edges, is just equal to V minus 1. And that's what a tree is. So a tree is just a special kind of graph. So when we talk about graphs, right, it's hopefully like a lot of the stuff we'll talk about today is just like a natural extension of what we've seen in the past. But nevertheless, graphs generally just have vertices and edges, and the number of them we indicate by the number of vertices and the number of edges. And so here, for example, we see the set of vertices is 1, 2, 3, 4, and 5, because these are our vertices. And the set of edges are 3 and 5, because 3 and 5 are connected by an edge. 4 and 5, 1 and 5, 1 and 4, and 1 and 2. Right, because 1 and 2, that's an edge. 1 and 4 is an edge. 1 and 5 is an edge. 4 and 5 is an edge. 3 and 5 is an edge. Oh yeah, and graphs are unordered as data structure. So like we saw maps last week are unordered. Same thing is true with graphs. There's no natural ordering, although you could order it somehow. But yeah, the number of vertices is 5, number of edges is 5. Okay, so connected graphs. I mentioned connected graphs, like trees are kind of connected graph. And all connected means for a graph is that all the vertices somehow connect to each other. So two vertices are connected. So there's a pairwise connection between two vertices if they have some path between them. So then we say they're in the same connected component. So for example, here on the left, we see that 4 and 2, right? There's a path that connects them. So you can go from 4 to 1 and 1 to 2. So there's some way to get from 4 to 2. So they're connected. Whereas here we say 4 and 2 are not connected because there's no way to get from 4 to 2. Like no matter what you do, you can't get from 4 to 2 by taking edges. So they're not connected. And also you can't get from 2 to 4. So they're not connected. And an undirected graph, we'll talk about directed versus undirected in a second. But an undirected graph is a connected graph. So if the followed vertices are connected. So if you can get from any vertex to any other vertex, then it's connected. So trees are connected graphs. So as we said before, it's just a special kind of connected graph. But if you can't get from some vertex to another vertex, like here, you can't get between 4 and 2, right? It's unconnected or disconnected is, I think, the proper term for disconnected. That's okay. So yeah, that's it for connected. Hope that makes sense. Now we'll talk about directed. So directed, usually with like trees and I guess with graphs, usually when we talk about them, or I guess the most natural way of thinking about them usually is just like if there's an edge between like 1 and 4, like we see here, right? That's just, you can go from 1 to 4 or 4 to 1, and both are completely fine. But with directed, we say, no, the edge only goes one way. So the edge, instead of going from 1 to 4, we're like, okay, it really only goes from 1 to 4. There's no edge from 4 to 1. So an undirected graph is really just a bidirected graph, like every single edge goes both ways. But with a directed graph, we can specify, right? Like instead of just every vertex or every edge connecting the vertices in both directions, it just means you can only connect in one direction. if you want to, but you can also still have both directions. Like this would still count as directed graph. But what that means, right, is that how we might think of cycles is slightly different, or maybe how we think of like connected is slightly different. That's okay. We'll talk about that too. But in any case, really the main idea is undirected. Every edge functions as like a path from like one vertex to the other vertex, and that second vertex back to the first vertex. Whereas with directed, it only goes one way. Now talk about cycles. So with cycles, which I mentioned the word a minute ago, but a cycle in a graph is a simple path. It's just like a path in a graph. So some sequence of edges starting at a vertex, you go through sequence of edges and reach something else. So it's just a path in which the first and the last vertex are both the same. And a cyclic graph has no cycles. So let's look at this. So this first one, right, is an example of an undirected graph, right? It's undirected because, well, the edges don't have like arrows on them. So we can think of it as going like each edge going both ways. And we say that this is doesn't have a cycle. It doesn't have a cycle because no matter where we start, right, we can't take a new edge. Like with when we say simple path, this means any path that doesn't repeat edges. So for example here, 1 to 3, we can't get back to 1 without taking the same edge again. And this one, 1 to 4, we can't get back to 1 without taking the same edge again. 1 to 2, we can't get back to 1 without taking the same edge again. And the same thing is true if we start at 2, 3, or 4. And because that's the case, right, there is no simple path that can get us back to where we started. So we say it's an acyclic graph. Another definition for cyclic graphs, I mean, this isn't necessary, just something that I find kind of interesting, sometimes it helps recognizing cycles, is that if you have an undirected graph, this is specifically for undirected, if you have two paths from any vertex, any other vertex, that will also, like separate paths, like they're distinct. If you have two ways of getting to one vertex from this same start vertex, then you're going to have a cycle in your graph. Although that's just like a different definition for undirected graphs for cycles. It's not necessarily something you have to know. The real takeaway from this is just what a cycle is. And it's just you have a path, a simple path, so you don't repeat edges, and you get from one vertex back to itself. With acyclic graph, with directed graphs, you can also have acyclic graphs, and they can look a little different. Because if these edges, for example, right, were undirected, then clearly we have a cycle, right? Because we can go from 1 to 4, 4 to 3, and then 3 back to 1. And that would have been a cycle. But because it's directed, it's acyclic in this case, because we can start at 1, we go to 4. We can't go anywhere else. We can't go to 3. So that cycle is no longer there. And it's the same thing if we start at 3, we can't go from 4 to 1. And if we go like 1, 3, we can't go back to 1 without taking the same edge again. Actually, we can't, because 4 has nothing you can get rid of. So even though this one may look like a cycle at first, it's not, because it's a directed graph, so you can't go back. And directed graphs can have cycles. Like if we also had, if, for example, instead of this edge going that way, if this edge went this way instead, like that, we can still have a cycle here because you go 1 to 3, 3 to 4, and 4 to 1. But as it is, this is a cycle. The last one is a cycle because, yeah, you can, for example, you can start at 1, go to 3, 3 to 4, and 4 to 1. So you don't repeat any edges, and you go back to where you started by taking some path. So it's cycle. That's cycles and graphs. And trees, yeah, trees are an example of any cyclic graph. So there you go. Okay. So for weighted graphs, all it means is that we just associate some weight with each edge. That's it. And a weight is just like a number. And with unweighted graphs, like kind of like how when we think of undirected graphs are really just graphs where every edge is bidirectional, so you can go both ways. Or you can just think of it as none of them have any direction. Weighted graphs, unweighted graphs, you can think of them as all having no weight, or you can think of all of them having weight exactly 1, because they're all weighted the same. You can just think of it as all having weight 1. But again, it may just be more natural to think of no weight. That's also perfectly fine. So here, every edge is like weighted the exact same. Like there's no ordering to how you might choose an edge, for example. But with a weighted graph, the edges have different values. They all mean different things. So like we may say that this edge between 4 and 3 is heavier than maybe the edge between 1 and 2 because it's 10 instead of 4. So we just assign some weight, and kind of like maybe geometrically we can think about it. Like if we're talking about a graph as like maybe these are cities, right? Like 4 is a city, 1 is a city, right? 2 is a city, and 3 is a city. Maybe we can think of these as like distances. Maybe it doesn't make so much sense if we have a negative here, but maybe we can still think about distances. Like the distance between 3 and 4 is 10, and the distance between 3 and 1 is 2. And maybe we can say it's like in the east direction or something. So then maybe -5 means it's towards the west or something. I don't know. But the point is like you can think maybe of these numbered weights as like distances in some cases. And yeah, it just means put some value on the edge. And you can really assign any value or any meaning depending on the situation. Okay, so here's a poll question. So if we look at this below graph, which of the following is it? Is it acyclic? Is it connected? Is it weighted? Is it directed?
Just weighted.
Yep, just weighted. Awesome. Right. Very good. So it's not acyclic because we can see a cycle here, right? 1, 5, and 3. And it's not connected because the 6 is off by itself, but it is weighted, as you mentioned. Awesome, because every edge has weight. And it's not directed because there's no arrows on the edges. Cool. Awesome job. So yeah, now we'll talk about graph representation. So there are 2 main ways in which we represent graphs. The first of them is adjacency lists. And adjacency lists are good for sparse graphs because the other one we'll talk about is adjacency matrices. And the problem with adjacency matrices, which we'll talk about in a minute, but the problem with them is that they tend to store extra information that maybe isn't so necessary when you have a sparse graph. And a sparse graph is when you have a graph without many edges. So like a tree, for example, is a sparse graph because it only has like v-1 edges. So it's considered like a sparse graph. In general, sparse graphs don't have many edges for the number of vertices they have. And adjacency lists are perfect for this because what adjacency lists do is they just say, okay, so for every edge, for every vertex, just store the other vertices that it's connected to, and that's it. So in this case, if we look at 1 here, right, in adjacency list representation, it's connected to 2 and 5. So its adjacency list will just contain 2 and 5, right? And it's saying, okay, this is what I'm connected to, 2 and 5. And then similarly, if we look at, let's say 4's entry in the adjacency list, right? It's connected to 3, 2, and 5. So we're going to see that. Right? And this order doesn't necessarily matter because as we mentioned before, right? There's no natural ordering for graphs. But it should contain 2, 5, and 3, and it does here. So this is how we represent it within an adjacency list. It's just every vertex just contains a list of the things it's connected to. And yeah, every combination of the outer list and nodes has an edge between 2 nodes. So like 1 and 2 are connected. And we should, because undirected, we should expect to be symmetric. So if 1 and 2 are connected, then 2 and 1 should also be connected, right? Because undirected graphs are kind of the same as bidirectional graphs, it should be both ways. And as it mentions here, if E is a lot less than V squared, then that's what a sparse graph is. So that's when we want to use adjacency lists. And the reason why we use specifically this is because a complete graph, which is a graph in which you have all edges, so like every vertex connect to every other vertex, you'll have something of order V squared. Like E is of order V squared in that case. Because like the first vertex you can say is like connect to n-1 other vertices, or v-1 other vertices. And the second vertex connects to like that we haven't counted yet, right? And then the second one is connected to like v-2 other vertices we haven't counted yet. The third one v-3, or yeah, v-3. And if we sum all those, then that's v-1 plus v-2 plus v-3, and so on. And we've seen that sum so many times. That's of order v squared. So yeah, if we have an adjacency list, like for if it's not a complete graph, right? So if not something where every other vertex connects everything else, then you might have something where there are not many connections between edges, like with a tree, and that's what we call sparse. But like, yeah, a complete graph, like all the edges are there, is not sparse. So I just wanted to like make the distinction why we're saying v squared is here, like rather than like, I don't know, v cubed. We choose v squared because that is the most you can have. So yeah, here we'll just kind of see an animation of this adjacency list to refresh you on what we talked about a second ago. It's 1 and 5. So we'll see that 1 is going to have 5 in its adjacency list. And the same thing will be true for 2, right? It's also connected to 2, so it's also in its adjacency list. Okay. So some adjacency list operations. If we want to check adjacent pairs, so if 1 is adjacent to 5, right? If we want to check that specifically, we have to traverse all of 1's list. We have to say, okay, is 1 connected to 5? Or is 1 adjacent to 5? What we do is we look at 1's adjacency list entry, right? And we go through all the vertices connected to. We have to traverse all of them. And if it's in there, perfect. It is adjacent to 5. And if it's not adjacent to 5. By the time complexity of checking that is equal to the out degree of 1. And out degree is like the number of edges coming out of it. So the number of things connected to. And we say out degree because like if it's directed, then like if it's directed, for example, then maybe only 2 is in its adjacency list, right? We wouldn't put 5 in here because there is no edge from 1 to 5. So that's what we call out degree because it's literally going out if it's directed. But this is undirected, so out degree is just any edge. Okay. Yeah, and since we have to check all of them, like all the things that 1 connects to, the worst case time complexity for it is the out degree of that vertex. So out degree of 1 is the worst case time complexity because that's how many things we have to check. And then in terms of getting the neighbors, what if we want to figure out which nodes 1 is adjacent to? Like specifically, rather than checking, oh, is 1 adjacent to 5? What if we want to find everything it's adjacent to? We have to still go through the entire list, right? We have to go through all the entire list, like everything that's connected to. We can, if we just want to print out the things connected to, we just print them all out. So worst case for this is the same thing. You just have to go through the whole list. So it's also out degree. That's just the number of things that 1 connects to. If we're looking at 1s, for example. Okay. So that's adjacency lists. Now we'll talk about adjacency matrices. So where adjacency matrices better, where they're worse. So dense graphs rather than sparse graphs use adjacency matrices. This is like, for example, look at a complete graph or any graph where there are like a ton of edges. We're going to want to choose adjacency matrices because they're generally easier to work with. And like they represent dense graphs pretty well. But if it's not dense, then maybe it's overkill because it uses a lot of extra memory. And the reason for that is because regardless of whether there's an edge between like some vertex A and some vertex B, even if there's no edge, we're still going to store some data about it. And what we're going to store is that there's no edge. So for an undirected, unweighted graph, what we're going to do is if there, or even if it is directed, if like there's an edge between 1 and let's say 2, right? Then in row 1, column 2, we're going to put a 1. And if there's no edge, let's say between like 1 and 3, right? There is no edge here, right? So we're going to look at row 1, column 3. There should be a 0 there. And there's a 0 there. That means no edge connects them. And if there's 1, it means there's an edge that connects them. So yeah, 1 and 5, right? 1, 5, we're going to expect there to be a 1. And let's say 1, 4, we're going to expect there to be 0. And again, this one's also symmetric because it's unweighted. For unweighted graphs, or sorry, for undirected graphs, adjacency matrices are going to be symmetric. Because again, it's just like it's almost bidirectional with the edges, such as why. So we like split it here, we would notice symmetry between 2 halves. That's kind of off topic. Anyway, if we look at like 4, for example, 4 is connected to 2, 3, and 5. So we're going to expect in its row, right, in this row here, we're going to expect 2, 3, and 5 to have a 1. And then we're going to expect 1 to have a 0. And 4 also is 0 because 4 doesn't have an edge to itself. So you notice 0 here and 0 here, and 1 here, here, and here. So it's kind of a nice way to represent it. I think it's a lot easier to work with because you don't have to deal with different sizes, and it's also just like nice to work with in code. But of course, like if we have something like a tree, right, where there are about the same number of vertices, the same number as edges, then this can kind of be overkill because you're using like v squared. Like this array is gonna, or this 2D array will take v squared memory, so the number of nodes you're gonna have squared. Whereas an adjacency matrix in that case will only take like order v. So sometimes adjacency matrix lists are better, but adjacency matrices are usually easy to work with. So that's one good thing about them. But anyway, moving on a little bit. So yeah, we use matrix to represent it. 1 if there's a connection from there to there, like row to column, and 0 if there's not a connection from row to column. But what can we do with adjacency matrices? Oh, well, first we're going to see this animation. So notice edge from 2 to 5. So row 2, column 5 is 1. Okay, so operations on it. We want to check adjacent pairs. Like we want to check if 1 is adjacent to 5, then it's actually really easy and it's a lot faster because we can just check, right? And if there's a 1 there, then it exists, and if there's a 0, it doesn't exist. So we can just check array 1, 5, and that's row 1, column 5. That just tells us, is there an edge from 1 to 5? Well, it's exactly what 1 there would mean, right? And we have like O1 access for arrays, so we don't have to go through everything. So just O1 time to figure that out. To answer this question, just O1 time, which is good. But the bad thing might be with, if we want to check all the neighbors, what 1 is adjacent to, we have to go through the entire row. So, or the column. So you have the column or the row. But yeah, what nodes is 1 adjacent to, we have to go through this entire row. And this entire row isn't just the out degree, it's all the vertices because we have data for all the vertices. So we have to check for all of them, is there a 1 or is there a 0? And for all of them, if there's a 1, it's something that 1 is connected to. So that takes OV time. Okay, so I think there's a poll question. So let's talk quickly for checking what a vertex is adjacent to in the adjacency matrix representation.
The second one.
Yeah, awesome. That's right. Exactly right. OV. Cool. Good job. Yeah.
I have a question about the matrix,
Yeah, of
which
course.
is if it's a directed graph, like which axis would be like the one we're going away from versus the one we're going to?
Yeah, that's a good question. You could do it either way, but the general, customary way to go about it is to just make like the rows the out degree. Like, so if one has if there's an edge from 1 to 2, then you would put a 1 here. And then for the column, you would do it differently. So if it only goes from 1 to 2, but not from 2 to 1, then 2, 1, you put a 0 here. So it's like row is out degree and column is in degree. If that makes sense. So like if it looked like this, oh, sorry, 1 to 2.
Yeah.
Then
No,
we put
yeah.
a 1.
Here's an example.
Yeah, so like here, we put a 1. Let me erase this. Yeah, we'd have like a 1 in this case from 1 to 2, and then a 0 in 2 to
Okay.
1.
Okay, thank you.
No problem. And for this one, yeah, you have to find check the entire row. So also, yeah, that was a really good question. So thanks for asking. Okay, yeah. So given the following adjacency matrix, what is the path from node A to node I?
The third answer choice.
So, yeah, exactly right. And yeah, we kind of see that. So Yeah, so what we can figure it out from just the matrix, as it looks like Rachel did, is you can go here and you realize, okay, A is connected to B, C, and D. So let's check all of those. So to B, C, and D, we check, are any of them connected to I? No, they're not. But for example, B is connected to E, which is then connected to I, which we see here. And so A, B, E, I does give you a path. And if we manage to draw out the graph using this matrix, then we'll actually see it a lot more easily. A, B, E, I. Cool. So now we're going to talk graph traversals. So graph traversals are just a natural extension of tree traversals. Like they may seem complicated, but they're really just the same thing. And even the code is almost exactly the same as we would do in tree traversal. So for graph traversals, we classify them in the order in which we visit vertices. So the traversal algorithms, main ones are ad hoc, which isn't really something that's used because that's just like randomly visiting. There's depth first search and breadth first search. These two are the main ones we use, and we saw them before with trees. If you remember in trees, we had level order traversal. That's just breadth first search. Yeah, breadth first search, level order traversal are the same, and like post order, in order, and pre-order are all examples of depth first. And if we remember from those, like with depth first, we used like in order, post order, and pre-order, we used like the call stack, and for level order, we used queue. Same thing here. We're going to be using a stack for depth first and a queue for breadth first. And time complexity for this is O of V plus E. And we'll see why in a minute. And traversal and search, as you notice, I probably said traversal versus search. Like you may hear both. They both are completely fine. Both mean the same thing. And here's kind of some drawings. Ad hoc, as you can kind of see, go kind of randomly. Depth first search, you keep going as far as you can in one direction until you can't go any further. And then you, once you hit a roadblock where you can't go any further, you backtrack. And breadth first search is just to go one further away each time. Anyway, so we'll talk more about depth first search here. So depth first search is at a given vertex, you visit the children before you visit the siblings. So you just go as far as possible in one given direction, so you can't go any further. And then at that point, you backtrack. So you go back to a previous vertex you've already visited. And if you can go further with that one in some direction, you do that. And you keep doing that. And then eventually you'll come back to it. And then you go back to its parent and so on until you get back to the root. And then you're done. Yeah, so you go as far down a branch as you can, and then at some point you can't go any further. So one way you can think of is solving a maze. Like even when we solve mazes, right? You go through until you hit like a dead end, and then you're like, oh, well, I couldn't go that way. So then you backtrack, go back to the last place where you could make a decision. And if that, because evidently your last decision was wrong, so you try a different way. And if that doesn't work, you go back to the last place made a decision. So the way a computer can solve a maze will be similar to how humans solve mazes in that regard. Where you just go as far as you can, and you realize you can't hit a dead end, you go back. On topological sort, there's something we'll talk about next week. That was something with like prerequisites is a good way of describing that, I guess. But we'll talk about that next week. And there's planarity testing. And yeah, not sure much about that, but I guess something a depth first search could be used for. Let's see some code for it. So as I mentioned, depth first search is an extension of depth first search for trees, in which you use a stack. So use a stack here too. And the way it works is you start with stack. You go through each vertex. So you start with a starting vertex. And then for every vertex you set, or for every vertex, you at first mark it as unvisited. So you set it to false. You say, okay, I haven't visited yet. Then you push your first vertex, the one you start with, which is the one that's given here, onto your stack. So probably that's the only thing on your stack. And then while your stack isn't empty, so while you haven't visited everything you can, what you're going to do is you're going to go ahead and pop the new vertex onto the stack. So U here is, yeah. Oh, sorry, you're going to pop off the stack. So we push onto the stack, we're going to pop the stack. So we're going to take U as like the first thing on the stack. So you're going to take the first thing off the stack. And if you haven't visited already, the market is visited. So yeah, originally everything was unvisited. So once we visit something, or once we actually like access it, the market is visited. When your market is visited, then you're not going to visit it again, because if you haven't visited it before, then you're going to get all of its neighbors and put them on the stack. That way you're going to keep going and getting neighbors until you've accessed like all of them, then you go back. But notice if you have already visited you, then you don't need to visit it again. So you just don't do anything. So yeah, that's kind of the idea of depth first search. It's the same thing with like with a tree, where we went as far as possible in one direction, just keep getting things, putting them on the stack. And once the stack is empty, you're done. But if you've already visited something, you've already seen a node, then you have no reason to access it again. So you just ignore it. And then the end. And as you may notice here, the time velocity is O equals C, because you're visiting every vertex, but you also have to visit every edge. And you visit every edge because in here, you make this, in this for loop here, you check all the unvisited neighbors W of U. So that's all basically that's depending on the number of edges that U has. And since you're doing that for every node, the total number of, you can have to that, because you're doing that for every node in the whole graph, you're checking every edge. So E, and then plus V, because this loop goes over all vertices. So you're checking all the edges, and you're also checking all the vertices. But you're not checking every edge for every vertex. It's not O of V times E, but you're just checking all the vertices, and you're also checking all the edges. That's O of V plus E. You visit each vertex once and each edge once. Hopefully that kind of makes sense, but we're doing a depth first search. Breadth first search. So with breadth first search, it's a little different. Because we mentioned with depth first search, you go as far as possible, right? Then you backtrack. Breadth first search, you don't do that, right? It's just like a level or traversal. You check all of the children before visiting any of the grandchildren, right? That's what we do with level or traversal. With breadth first search is exactly the same. You just visit all the neighbors. Like if you have a starting vertex, you visit all the neighbors of that starting vertex before you visit anything that's 2 away. So if I'm starting, let's draw it out, I guess. Like if I have this vertex and it's connected to this guy and this guy, and each of those, maybe I'll even draw it kind of as a tree, but not quite, right? I guess I won't. So if it's not like this, if I start here, I'm gonna visit this guy and this guy before I ever visit this one, this one, this one, or this one. So you always go 1 away before you go 2 away. And some examples are finding the shortest path in a graph, and also BFS of the tree from, in this case, like BFS of the tree from BFS on German cities. So here it's weighted, but don't worry so much with weight. Here again, weight is distance, but the way we're gonna check, right, is we're just gonna go ahead and go to the things which are closest first. So starting in Frankfurt, it's gonna check this one, and this one before it does anything else. So notice these are all at the level above this one, which indicates we're going to visit things at like level 1 before we visit things at level 2 or level 3. Because that's what breadth first search is all about. Okay, so how do we write code for this? Again, exactly the same as we write code for a breadth first search in a tree, because that was just a level or traversal in here, and there we used a queue. Here, also a queue. Code is almost actually exactly the same. And what we do is we start with our graph and our vertex we want to add, right? So we start with an empty queue. We add to our queue our new vertex. Market is visited. And while our queue isn't empty, we take it off the queue and check all of its neighbors. Rather than getting its 2 children, notice that's the difference. With the lower traversal, we got the 2 children or n children. Here, we just get all the neighbors, but it pretty much is the same thing. We get all the neighbors of W of V, so we get all the neighbors of our new vertex that we just remove from our queue. If they're not visited, add them to the queue. And then mark them as, mark that new vertex is visited, so that way we don't add it to the queue accidentally in the future. So basically just use a queue. and add things to the queue as you go along and mark the vertices visit. So almost the same code. And notice here, we're also visiting all the edges because in this inner loop here, to figure out what the neighbors are, we have to figure out, it's dependent on what it's adjacent to. So what there's an edge between. I visit each vertex once also because in this outer loop, notice that while the queue is empty, we only dequeue once in the while loop each time. So if presumably we're adding every vertex into the queue at some point or another, and each loop we're only like dequeuing once. So the total number of times we're going to dequeue is v. So we visit every vertex at one time. And we also see each edge one time. So it's OV plus E. So both of them have the same time complexity, but notice that there are problems that breadth first search is better for and depth first search is better for. And that's okay. And we'll kind of see in a minute when one might be better than the other. But first, which data structure, actually even better, which data structure would you use for BFS and DFS? Oh, yeah.
BFS is stack and DFS is queue.
I think.
I mean, the backwards, the other
yeah,
way.
yeah, you got it right. I think, yeah, because we went over them the opposite order. But yeah, perfect. Yep, BFS is queue and DFS is stack. Awesome. And so now we'll see when might it be good to use breadth first search? When might be used to use depth first search? Well, okay. So let's talk first about problem solving using traversals. So about this one, right? Flood fill. So flood fill is something like if you use like Microsoft Paint or something, you might have seen this before. It probably is Microsoft Paint. I don't know really. I don't really use Microsoft Paint, but I'm assuming it is. Anyway, flood fill is used in a bucket fill tool of paint programs to fill connected areas. So in this example, let's just watch the animation, see what it's all about. So we start with empty. Let's say I click on this one, let's say region here, and it highlights everything red, and it kind of expands outward. And then when I click on the other one, let's say, right, it's going to expand outward with blue. So we can write an algorithm that performs the flood fill program using breadth first traversal. And okay, so we can kind of think about how we can do this. But with breadth first, right, we're going to go out further and further until like we visited everything. So rather than just like going in one direction, and that's exactly what we see here, right? We don't see, like if it were depth first search, then what we might see is if I like clicked here, right, it might go all the way in one direction rather than like it might go in one direction all the way, right, before it ever comes back and does this way. Whereas with breadth first search, we click it and it'll go further away and then further away and further away until the whole thing is filled. So maybe we can think about the code. And you noticed, actually, I don't know why it highlights breadth first search here. It's on the last slide, but that's fine. Yeah, and the whole idea is each pixel wants to fill all the same color pixels around it before it expands. So you color all the things around it, then you go further up. And this is just breadth first search. You don't color pixels that were different color than the start. And yeah, because that way we kind of have the edges, like the boundaries here with the black circles. And as for code for it, really, this is just not too different than the code for breadth first search. It really is just the breadth first search code, but it's really just pseudocode here. So for flood fill, you start with your node, start with your target color, and you have your replacement color. So if the target color is equal to the replacement color, you're done, because you don't need to recolor that vertex, because you already recolored it. If the color is not equal to the target color, I'll return, because that would mean like you hit a boundary. If you hit a boundary, don't color that. Otherwise, it's not a boundary, and it hasn't been colored yet, so we're going to color it. So what we're going to do to color it is we're going to set Q to be an empty queue. We're going to add the node to the end of the queue. So we're going to basically say, okay, this queue, or this vertex, sorry, is going to go into the back of the queue. So we're going to color it. And while the queue is not empty, get all of the neighbors of this vertex. And we're going to set n equal to the first one in the queue. So we're going to move from the queue. right? We're gonna remove this first element from the queue, find all of its neighbors, add them to the queue. And in this case, right, we're assuming there are only 4 directions, so we're gonna check the 4 directions. So the west, east, and south. And what we're gonna do is we're gonna set their colors to the correct value, which is the replacement color, and then add them to the end of the queue. So that would be, we keep going. So it's the color of the node to the replacement color, and add the node to the end of the queue. So the neighbor node, we're gonna add to our queue, and we're also gonna color it itself. And if there are 4 directions, we just use for all of them. We keep going until our entire queue, until the queue is empty, and we return. So really, this is basically just breadth first search, but just with coloring and 4 directions. All right, and the next one we're going to talk about is actually shortest unweighted path. So if we're given the edges of an undirected, unweighted graph, so that's pretty much the graphs we're working with today. And that's probably the most common type of graph to work with, to be honest, or I guess simplest. They're definitely, it depends on what you're doing, but probably the one you'll see the most. There's undirected, unweighted, and 2 vertices U and V. In the graph, right, an algorithm that computes the minimum number of edges between them. So basically find the path in an undirected, unweighted graph. Find the path that goes through the fewest edges, right, to get between them. So assumptions you can make are that there will be at least one path. There exists a path. Anyway, so your input in this case, you're getting an adjacency matrix, right? And you get your 2 edges, or sorry, 2 vertices. And you want to find what's the shortest path between them. So in this case, the output is 2, right? Because we notice the shortest path is from U to W, W to V. There are other paths like U to D to N to W to V. That's another path. But looking at this one is definitely actually kind of tricky to think about. I think like figuring out which might be better, breadth first search, depth first search, but maybe you can think to yourself like, okay, which one is better here, breadth first or depth first? And if you're here, then you can answer it if you have an idea.
I think it would be breadth first search.
Yeah, awesome. Yeah, go on, why?
Yeah, when you're like, since it goes in every direction like the equal amount at a time, we won't have to bother going the rest of the way for a path that would be longer.
Right, that's exactly right. Yeah, perfect. Awesome. That's great. Yeah, so it would be breadth first search. And we also don't have to worry about doing something like this where we accidentally go like the wrong way super far and then have to backtrack. And then we're like, oh, there's another way. We don't have to worry about that because once we found something, right? Once we found something, because we go shortest path, shortest path, shortest path. Once we found something, we know we're done. So let's see the code for it. We use BFS. And so we create a queue and put U into it and mark U as visited, our queue. So originally we start with our edges, right? So we have the distance from like V to, or U to itself is 0. And yeah, we have distance and 0, and we have our queue. So we're going to push into our queue U, which is our start vertex, and we're going to mark it as visited because we visited it now. And while our queue is empty, we're going to take the first thing from the queue and remove it from our queue. And then we're going to go through all the edges of this vertex that we removed from our queue. And if we haven't visited already, we haven't visited edge xi, so if we haven't visited its neighbor, then we're going to say, okay, the distance from the start, or distance from like, the distance in order to get to this vertex, right? From the distance to get to this vertex is the distance it took for us to get to the previous vertex along the path, right? Plus 1. And then we mark it as visited, and we add it to our key. Because if we think about it, let's just go back a slide. If we were actually to do this, right, then what would happen is, just going with this example, U to D and look at U to P and U to X. We would do all 4 of these first, right? These are the 4 we would do first. I don't know why I drew it like that. Let's just do it like this. These are the 4 we would do first. And when we do these, right, the distance from U to X is 1, U to W is not 2. It's just since here's also 1, right? And here's 1, and here's 1. And when I say distance, I mean that's the number of edges we have to go through to get to like each of these. It takes 1 to get to x, 1 to get to Zoe, 1 to get to B, 1 to get to B. And so now we go 1 further away, right? And when we do that, that's going to mean that, okay, it's going to take total, it's going to take 2 to get to C. It's going to take 2 to get to C because it was 1 to get to P, but now 1 more to get to C. It's going to take 2 total to get to N, 2 total to get to V, and 2 total to get to M. Because we're just adding 1 to the distance took to get to the guy before it. And we know that this is also the shortest way. If we haven't already visited, let's say we haven't already visited M like we hadn't before we went from W. If we hadn't already visited M, we know this is once we found some path to get to M in a depth or in a breadth first search, it's the fastest way or it's the shortest way to get to M because there can't be a shorter way. Because if there were, we would have already seen it, right? Because we already saw all things that were 1 away from you. Now we're seeing all things 2 away from you. Well, M can't be 1 away from you because we already checked all things 1 away from you, and it wasn't one of them. So once we've actually assigned, and that's part of the reason why once we've like assigned a distance, we actually can mark that as visited, and then we never have to visit it again. That's part of the beauty of breadth first search for this kind of problem. We can't do that for our depth first search here because we don't know if there's a shorter way. And so that's really a nice consequence of using breadth first for this kind of problem. And then once we've actually found, one thing we could do is once we find some path, like once we actually give a value to u in this for loop, like once we actually find the distance like from u to v, if we actually find v somewhere in there, we can just terminate and return it there. Alternatively, like we see here, we can just like record the distances and just return it at the end. And that's also completely fine. We can also terminate this early, possibly. When I say possibly, I mean it may not happen every every single time you call the function. It may not find it until the very end. But you could absolutely put like an early termination in here, but you don't necessarily need to. Either way, you just return at the end. Anyway, you just return distance to v. That's it. And yeah, while the queue isn't empty, you go through every edge in the queue and increment the weight of all the vertices. So you're just using a breadth first search. And again, code is very, very similar to just the regular breadth first search code. But okay, there is another kind of problem we can do here, which is counting the number of islands. So if you're given an m by n 2D binary grid, which represents the number of 1s and 0s, arbitrary number of islands, an island is surrounded by water and is formed by connecting adjacent islands vertically or horizontally. And you can assume that all 4 edges of the grid are surrounded by water. So basically, the goal of this problem is if you're given like a matrix like this, you want to figure out, okay, how many different islands are there? How many different like regions made up of only 1s, right? That are surrounded by completely 0s or boundary. So maybe you can think, okay, well, would a BFS be better here or DFS be better here? That'd be tricky, but any ideas? It's okay if not. So yeah, for this one, we're going to look at it and we're going to say, okay, well, one way we can think about it is, okay, well, this one here, right, this island here, right? Maybe I can, oh, okay. So one way you can think about it is that like we start with some point here, right? And we can just keep going. We want to keep going until we finally, we want to find the boundaries of the island first. That's one nice kind of way of thinking about it. So we can go as far as we can to the boundary in both directions. And what that's going to do, if we do that from this vertex, right, then we can do that recursively. So now we can do that on this vertex. So you go as far as possible until basically until you find the boundaries of this. And once you do that, you know that's the end of that island. So now you can start on the first thing, which you haven't already seen yet, right? The next start to a different island. And maybe this kind of looks like one of these searches. And maybe not, but that's okay. It's really a depth first search. And the way that is because we're kind of looking for, okay, as far as possible one direction, check out the boundary. And generally, questions like this with island, it's a lot easier to write code with a depth first search. Although pretty much any problem, it's okay.
Sorry, so I had to step away for a second, but it came back. For this question, so is it just asking for like this, like the total number of islands, not in any like path?
Yeah.
Okay. So, with a like, is there like a big difference doing it either way with breadth first or depth first, since you have to go all the like check every single spot anyway?
Yeah, so you're exactly right, and that's something else. But yeah, exactly right. There, you could use either one. Like in this example, the one that isn't necessarily fast, and the other depth first is probably easier to write the code for. So
okay,
depth first is probably better.
Yeah, that makes sense to me.
But yeah, but absolutely, both are completely fine. Yeah, and so we can check. Listen to the code.
Okay, thank you.
No problem. So yeah, we can use DFS, but absolutely DFS would also work here. And so we might do this is we're given our grid, right? And we check over all of the indices of the 2D array. For everyone that's 1, we increase the number of islands and call a DFS function. So originally, we have number of islands could be very large, right? Because what we're doing is we're basically just going over all of it. Sorry. Oh, yeah. So we start here in our num islands. And yeah, we're going to first start with our grid size. If it's just 0, then we're return 0. And then we get these as the first row. First column. First column, we start with num islands equals 0, but we increment num islands because originally we can think of it as, oh, well, we haven't actually, like basically every time we see a 1, right, we're starting an island and we're going to go ahead and visit all of the neighbors of that island, right? All the neighbors, or we're going to start with something that we know is in an island. We're going to visit all the neighbors. We're going to find everything in that little island, right, and mark it. And so then that constitutes one island. And the way we're actually going to do that here is by marking it. It's setting it to 0. That's just the mechanism by which we're going to do that. Any other way, it's fine. But then let's say we haven't. Let's say that there's some other island or some other thing marked as a 1, which we haven't already seen. That's still going to be a 1 after this code finishes, right? After we do our DFS, it's still going to be a 1. Like we haven't ever marked it as visited. And if that's the case for any vertex in our graph, then it's part of a different island because the DFS is going to check everything that surrounds it, each of the 4 directions. And it's going to say, okay, well, if you've ordered it and you're an island, then you're part of the same island. But if we've done that for everything in that island, then this other vertex couldn't be part of that island. And if that's the case, it has to be a separate island. So we call DFS again with that as our start. That's kind of the idea. So we start for DFS, we can get our column size, our row size, and this just allows us to say, okay, is it in bounds? Like these checks are just, is it in bounds? And if it's not in bounds, then like if the thing that's row -1 is not in bounds, or row +1 isn't in bounds, like these are just bounds checks, which we handle as just being a 0, right? Because 0, we said we can just say everything around the whole thing is sea instead of island or water. I don't know what word we use. But anyway, these are just bounds checks. And then these over here, these over here. This right here says that if it's land, right? Well, we called DFS on something that was land in the first place. So what this is saying is that something that our land borders is also land. That's part of the same island. So what we're going to do is we're just going to say, okay, now set that to 0, because what we want is we don't want that. When we go back to this if statement, we don't want num islands to increase when we see that 1. So we're just going to say, okay, anything that's part of the same island, just mark it as a 0. So in the future, we've already checked it, right? That's how we're going to do that. And that's why this line occurs. But anyway, what we're going to do is we're going to say, okay, For the thing that's to the row minus one, so the thing that's above it, called DFS, and mark that as 0. Then do that with all of its neighbors. And then for the thing below it, do the same thing. If there's a 1, if there's not a 1, then we don't need to worry because that already is like water, right? It's not island, part of the same island. And do the same thing for column minus 1. So things to the left and then things to the right. And it's just going to keep going outward, and it's going to keep going outward in one direction before ever going back and then going outward in a different direction. And obviously we could do BFS as well. DFS is a little bit nicer code because you can use the call stack really nicely. You don't have to worry about like using a queue. You just say, okay, call DFS. So you start at this one, you're going to go as far as possible. Then you're going to come back and backtrack. And yeah, so basically all of the row minus ones are going to happen before you ever check like a row plus one. But because the order doesn't really matter here, it's a lot easier to just use this kind of thing. And yeah,
it would be harder to keep track of like if it's the same island for the BFS.
Right. Yeah, that's exactly the point.
Okay.
Yeah. Mm-hmm.
I see.
Awesome. Cool. And yeah, DFS function recursively makes the non-zero vertical and horizontal neighbors 0. So we don't count them again. That's what we're mentioning about line 7 here. So that's about it for this problem. Yeah. Do you have any questions about anything?
Yeah, actually something in the very beginning,
Yeah,
which
sure.
was, it was, wait, can you go back to like some of the early slides?
Absolutely, of course.
I think it was with the, not with the matrices.
Adjacency lists.
No, I'm sorry. I think it was, yeah.
Okay.
No,
Yeah.
it was something about it was an order of something, and it was like out neighbors.
Oh yeah, yeah.
I don't.
Yeah, out degree.
Okay, yeah.
Is that what you meant?
So for the order for the out degree, well, I'm confused about the order here. Like, is it saying out degree times?
Oh no, it's just
vertexes.
It's just putting an asterisk here, so it tells you what out degree means.
So is the out degree just of this vertex? It's just saying of this vertex.
Oh yeah, of this vertex, right? And in the worst case,
okay.
That really is just the number of vertices. So I don't really know. Yeah, in this case, yeah, it could just be out degree of 1 for this case. Out degree of like vertex 1.
Okay, that's all. Okay, thank you very much. Have a good evening.
Yeah, thanks, you too. Bye. Bye, everyone.